Hey guys, this video today is going to be about ortho and para directing groups on aromatic compounds. We're going to explore why certain substituents cause, say, an attacking electrophile to add ortho or para to that substituent. Overall, there are two main factors we need to consider. The first one being carbocation stability, and the second one being the number of resonance structures. Just as a quick reminder, must remember that a tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary carbocation. Why? This is due to hyperconjugation. Please read up about that if you're not familiar. Second thing is the number of resonance structures. As you may know, we can create several different resonance structures of different compounds. Just as a quick example, we could have a carbocation that looks a bit like this, and because there's a lone pair on this chlorine, we can draw a resonance structure as such. And this, like I said, will be an important factor later on. So first of all, we need to look at the actual attack, the mechanism behind, say, an electrophilic aromatic substitution. I'm going to talk about the ortho position in toluene. However, if you're familiar with this and you're fine with that, please continue on about a minute or so, and that's when we're going to compare all the different positions and say why the ortho and para are favoured. So I'm going to talk you through this mechanism of the ortho attack. Well, I've got these hexagons down here, and I'm going to draw in our toluene structure. We have an electrophile, which means it likes electrons. If the activation energy has been met, we can break this double bond, depicted by the Kekule structure. As we know, it's not actually a double bond. And this can form one of these resonance structures that we've been talking about. So we've got the electrophile that's attacked there. We've also got the hydrogen, got this toluene substituent, and now we've got our carbocation here. Still got our two remaining bonds. Like I said, resonance structures, so we can push that pair of electrons there and move the cation around. Still got our two double bonds in here. Not forgetting our double-headed arrow, just to say that it's a resonance structure. Once again, we can move this charge around and we will have something that looks like this. Carbocation now placed on this carbon, electrophile there, hydrogen still there, and our toluene substituent. Then we can have a base that attacks the hydrogen and reforms the double bond as such. That goes to our final product, which is the toluene substituent and the electrophile, not forgetting our side product there. As you can see, this is the mechanism behind the ortho attack. And what we want to do is we actually want to compare all these to see why it attacks ortho and para and not meta. Well, here we have the ortho, here we have the meta, and here we have the para mechanism. As you can see, they both have three resonance structures. So looking at the two main factors I said at the start, it's not going to be number of resonance structures, but it's going to be carbocation stability. If you remember, I said tertiary is more stable than secondary, which is more stable than primary, like I said, due to hyperconjugation. Here we have a secondary, secondary, and tertiary. Here we have secondary, secondary, and secondary. And here we have secondary, tertiary, and secondary. So overall, we've got 2, 2, 3, 2, 2, 2, 2, 3, 2. So overall, this is more stable, this is more stable, and this is less stable. Hence, ortho and para positioning. What you may expect to see is in the ortho position, 66% this, say 33% this, and say 1% this, as the meta will still occur, just very, very unlikely to happen, but we still get a low percentage. Why 66 and 33? Well, we have two ortho positions and only one para position, but in reality, we don't actually get that. It would be something more like, these are just made up numbers, they're not actual values. It would be something more like 50%, 1%, and 49%. Why? Well, just simple steric hindrance. As you can see, we've got some hydrogen sticking off here. If we have a bulky electrophile, well, we can get steric hindrance here, and that will reduce the amount of the ortho position we get. to a more even number. It may not exactly be this. Like I said, these are not exact values, but it's just to demonstrate the point for you. Okay, now we're going to go on to the second point I was talking about, and this involves a number of resonance structures, and specifically lone pairs, substituents with lone pairs. Once again, I'm just going to quickly take you through the mechanism. If you're happy with this, skip forward about a minute or so, and we'll look at the different resonance structures for the different attacks and why ortho and para is favoured. Once again, we've got these hexagons get down here so we can draw our substituent on a benzene ring. Electrophile, once again, likes electrons, so we can attack it here. We can break that aromatic ring. We can draw several different resonance structures. First of all, placing the cation here, and we can move, say, this bond below down, and move the carbocation to here. And then we can move this double bond round, move the carbocation to this top carbon, not forgetting where the double bonds are now ending up. Not forgetting our double-headed arrow to say it's a resonance structure. However, this time, as you may remember in toluene, that's where it would stop. However, we now have a lone pair on this oxygen. This lone pair can now come down and form a bond to relieve that carbocation as such. And this forms a structure that looks a bit like this. So you've got OMe with a plus charge and a double bond to that carbon. We now have 3 bonds on that oxygen, hence the plus charge. And we've still got our hydrogen and electrophile here. As before, we can have a base that comes in, attacks that hydrogen, bond reforms on that aromatic ring, which is a big driving force. You want to reform that aromatic ring, and then that pair can move up to there, and that forms our final structure, methoxybenzene with an electrophile of some sorts, not forgetting the other bit of the reaction. So overall, that's the ortho position attack involving a substituent of lone pairs. Now if we look at the comparison of the ortho, meta and para position, as you can see here, we've got 4 resonance structures. Here we have 3 resonance structures, and once again here we have 4 resonance structures. Why do we have 3 here and not 4? Well, as you can see, we never ever get a carbocation right by that oxygen, so the lone pair cannot actually attack in, as obviously on the ortho and para, as you can see displayed, we do. Once again, why may we not get 60%, 66% this, and say 33% this? Well, methoxybenzene, depending on the electrophile, we can get the sterical hindrance in there, and that will lower the percentages down a little bit. Hopefully you found the video helpful. Please like and subscribe for more. Please share it with your friends if you found it helpful, and good luck on exams. Thank you.